Well, hi there. Did you know about the giant landslide in the subsurface of West Texas? That's the topic for today. I am Robert Font, a certified professional geologist and a proud member of the AIPG. The deformation that I will describe for you here today involves the detachment and lateral displacement of a massive earth block with a volume of 2,173 cubic kilometers and a lateral displacement of 10 kilometers. The mechanism for this very large, massive translational rock slide is one of gravity sliding that took place in the Delaware Basin of West Texas. The Delaware Basin is the western part of the Permian Basin, the latter being one of the most productive oil and gas provinces in our country. In the years that I worked for what is now ConocoPhillips, I spent about 4 years as a project supervisor in charge of the Delaware Basin. I can attest to you that this is a very complex area from a structural geology point of view. It is bound on the north by the Northwestern Shelf, on the east by the Central Basin Platform, on the west by the Diablo Platform, and on the south by the Ouachita Marathon thrust belt. The Delaware Basin started out as an olocogen in the late Precambrian to early Cambrian time. In terms of the structural deformations that you see in the basin today, I can tell you see the whole spectrum of what you can imagine, from faulted anticlinals to normal faults to horse blocks, grabens, some significant wrench faulting, high angle thrusts, low angle overthrusts, and some significant major unconformities involving repeated and even inverted stratigraphic sections. A structurally complex area of specific interest for us here today is out of the northeast portion of Pecos County, involving two fields, two oil and gas fields, Cayanosa Field and Rojo Caballos Field. Cayanosa is a pronounced faulted anticlinal structure with a system of west-bounding faults. Production is also controlled by porosity and permeability barriers. The estimated ultimate recovery for this field makes it a Class A gas field and a Class B oil field that approaches the Class A category. Rojo Caballos Field is another anticlinal structure that is faulted on the west and on the southern sides, with porosity and permeability barriers also controlling the production. The estimated ultimate recovery for this field makes it a Class B gas field, almost approaching a Class A category. Going southwest from Cayanosa Field towards Rojo Caballos, one passes a system of west-bounding faults. In the schematic cross-section that you see here, the mobile well, which is a productive gas well, lies on the anticlinal structure that defines Cayanosa Field. But then you go through that system of west-bounding faults. And when you reach the Williams El Chato well, now you have a dry hole here, but the importance of this well is the structural complexity that you see here. Below the Wolfcamp, you have 3 repeat Mississippian limestone sections, with the middle one actually being inverted. And those overlie the Wolfcamp. In this area, also a major translational gravity rock slide is recognized, masking the underlying structures. Once you get to the Rojo Caballos field area, the slide block is clearly seen. I'm showing you 2 wells here, the Rodan #1 McIntyre and the Pogo #1 Page Royalty. The Rodan well is an oil producing well. The Pogo well is a gas producing well. The wells are located about 1 kilometer apart. Well, at about the same subsea depth, we see the base of the slide block, where you have Permian Wolfcamp and Mississippian limestone overlying the Permian Wolfcamp. The West Texas landslide was first recognized by Guinan in 1971. So he takes the credit for this. Pinero, Risser, and Horak in 1986, Hanson and Guinan in 1992 also talked about this slide. What the authors visualize is a large-scale gravity rock slide occurring in Permian time, in Wolfcamp time. The slide bisects Cayanosa Field. The slide comprises all of the rocks above the Devonian Woodford Shale, where the Woodford Shale defines the actual detachment surface. This is a big landslide, a length of 23 kilometers, a width of 21 kilometers, a thickness of 4.5 kilometers, a lateral displacement of 10 kilometers, and the slope of the sliding surface about 2.5 degrees. The authors state that the base of the slide block was the thick, competent Mississippian limestone sliding over the top of the Woodford Shale. The authors also state that thick Permian and Pennsylvanian conglomerates shed from the rising Central Basin platform to the east, plus the steepening flexures on the western side and southern flanks of Cayanosa Field resulted in the gravity slide. Well, let's talk for a moment about the mechanics of the landslide. The horizontal stress sigma h required to move the block is given by the equation that you see here, where L is the length of the block, P is the average density of the rocks involved, G is the acceleration of gravity, mu is the coefficient of friction along the slip surface, and theta is the angle of the slope surface. Keep in mind that the crushing strength of sedimentary rocks ranges from 10 to 80 megapascals. If you translate that into dyne per square centimeter, the range is from 1 to 8 times 10 to the 8th power. Take the highest number. When you plug that number into our previous equation, then you can solve for L. What you're actually doing is you're solving for L max, the maximum size block that you can move under those conditions. And that's the last equation that you see here on the slide. All we need to do now is plug in the values for our slide block. We know the length, we know the width, we know the thickness, we know the slope of the sliding surface, we know the density of the rocks involved, the acceleration of gravity is a constant, and our last parameter here must be the coefficient of friction. Well, the accepted coefficient of friction between the Mississippian limestone and the Woodford Shale is 0.50. If we plug these values into the equation, we come up with a value of L max, which is 6.77 kilometers. Well, that's not going to do it because that's only a quarter of the size of our slide block. So to move our 23-kilometer block, we have to determine what value of mu, what coefficient of friction will allow us to do this. So we can rearrange the equations so that we can basically solve for mu. And once we plug in the values for our slide block, we come up with a value of mu equal to 0.176. That coefficient of friction would allow us to move the block. So what are the resulting implications of what we have done? Well, this highlights a series of factors that we need to consider. For example, what conditions existed in Wolfcamp time, in Permian time, along the western edge of the Central Basin Platform that would allow us or prompt the detachment of such a gigantic block, moving such a large horizontal distance? What was the nature of the sliding surface itself? What was the magnitude of the pore fluid pressures that develop in the Devonian Woodford Shale, and what would give rise to this? What were the actual dynamics of the movement? What event triggered the landslide? And what evidence of this event may come to light when we inspect or study nearby well logs, core and sample data, and seismic records? I should mention to you that a coefficient of friction of 0.176 compares well to those that we have determined for several landslide failures that we find in Japan. One of these is the Nigawa landslide that took place in 1995 as a result of the Kobe earthquake. It has a similar coefficient of friction. But the difference between the Nigawa landslide and our West Texas slide block is the volume of the rock involved. Our West Texas slide block has a volume that is 20 million times larger than the Nigawa landslide. 20 million. Wow. I think a better analogy for the West Texas slide block is the Storegga landslide that occurred in Norway approximately 8,000 years before present. Both landslides are huge. Both are examples of submarine mass wasting. More than likely, an earthquake triggered both events. It is not hard for us to envision some degree of sediment liquefaction and a pore fluid pressure buildup, possibly due to the abrupt breakdown of methane hydrates. In West Texas, a tsunami must have taken place or ensued just as it happened along the offshore coast of Norway. You know, in the Storegga landslide, tsunami-derived sediments are actually found in Scotland. Now, these are mechanical considerations, if you will, but there are some geological questions that we need to think about also. The only high standing area and potential source for our slide block is the Central Basin Platform that lies to the east. What if I tell you that the Carboniferous strata that is contained in the slide block is missing from the Central Basin Platform in our critical area? It's not there. Well, the conventional train of thought is that the strata is absent due to erosion. Now, that's a very logical and well-educated assumption. But is the explanation really that simple? Or is there more to it that we still do not understand? In summary, I can tell you that the calculations, what did this for me is it helped me with my thinking process, and it helped me visualize such an impressive deformation event. It also made me realize that my understanding of the slide block is less than what I initially thought. And it brought up additional possible topics of research for us to follow. Well, that's it. I hope you have enjoyed it, and I hope you have learned something. Take care, and see you later.